we are working on properties of logarithms. So one of the first properties of logarithms translates the log of a product. Log of m times n is the log of m plus the log of n. Now we've been saying last time emphatically that the log is the power, and so we know that when you have x to the m times x to the n, then you add the powers. And so when you have a product of bases with powers m and n, you add the powers. And this is all we're saying here. That the power of a product is the sum of the powers. So remember, x to the third times x to the second is x to the fifth. So when two powers interact through multiplication of the same base, you add the powers, and this is just a restatement of that. The logarithm of a product is the sum of the logarithms. And as you might expect, for the quotient, in other words, for division, something analogous happens. So the log of m over n, again, if I had x to the seventh over x to the fourth, the log is the power. And so the quotient of common bases results in you subtracting the powers. And so the way that's translated in logarithmic form is that the log of b, log base b of m over n, is log base b of m minus log base b of n. And we're going to be using that a lot today. So the log of a quotient or the log of a ratio is the difference of the logs. The log of a quotient is the difference of the logarithms. Similarly, or analogously, when you have x to the third all to the seventh, that is x to the 21st. You multiply the exponents. The logarithmic analog to that is that log base b of m to the p. You can bring this p as a power on m, and you can bring the p in front to turn into multiplication. And so log base b of m to the p is p times log base b of m. And therefore the logarithm of a number with an exponent is the product of the exponent and the logarithm, because here it was the product of 7 and 3, but 3 is the log. So it's the product of the power and the logarithm. It's the product of the exponent and the logarithm of that number. We'll also learn about the change of base formula. The change of base formula says that if I want to know, and the change of base formula is important because it allows you to find any base using your calculator. So on your calculator, you have this base, the log base, which is, and there's no base here, so that means it's base 10. And you have this one, the natural log, which is log base e. So if you wanted to know log base b of m for any b and any m that's allowable, then you can just do log base a of m over log base a of b for any a. Right? And so that would be which choice? And I'm liking, is there a choice E? I don't like any of these, except for the last one, choice D. So that's precisely what choice D says. That is the change of base formula. So why is this important? Because if I wanted to know log base 7 of 12, then you can put in your calculator log of 12 over the log of 7. Or you can put the natural log of 12 over the natural log of 7. You can always find the log of any number to any base by using the logs in your calculator. And that's why the change of base is nice in that way. All right, now let's use some of these rules. So it says use the properties of logarithms to expand the logarithmic expression as much as possible. Where possible, evaluate the logs without using a calculator. So it says log base 7 of 5 times 11. And we just learned that log base b of a times b is log base b of a plus log base b of b. In this case, little b is 7, capital A is 5, and capital B is 11. Therefore, this is equal to log base 7 of 5 plus log base 7 of 11. And we'll leave it just like that. Similarly, down here, this is equal to log base 7 of 343 plus log base 7 of x, except for, well, with one exception. That log base 7 of 343 is actually something we can reduce. Now, log base 7 of 5 from the previous problem, log base 7 of 11, we just have to leave those things like that. But for us, log base 7 of 43, 7 to the third, actually turns out to be 343. And therefore, if the log is the power, and it is, then this is asking for the power you raise 7 to get 343. And we just saw that that number is 3. Log base 7 of 343 is the number 3 because 7 to the third is 343. So the answer can be simplified to be 3 plus log base 7 of x. That is the answer for this. So for this problem, look out that this might be able to be simplified. Similarly, here we just learned that log base b of a divided by b is equal to log base b of a minus log base b of b. So again, division turns into subtraction. And so log base 9 of 9 over y is equal to, a in this case is 9, capital B is y, little b is also 9. So this is equal to log base 9 of 9 minus log base 9 of y. And there's no way in the world we would leave log base 9 of 9 the way it is. We know that the power that you raise 9 to in order to get 9 is a very beautiful one. And so we'll remember that log base b of b is 1 for every allowable b. So that this is 1 minus log base 9 of y, and we'll enter that as the answer. Similar problem from number 8, again using the division rule. Is equal to log base 5 of 625. Again, division turns into subtraction. Log base 5 of 625 minus log base 5 of y. Now the power, how many 5s are there in 625? 5 times 625. Log base 5 of 625 is 4. It takes 4 5s to be multiplied in order to get 625. So log base 5 of 625 is 4 minus log base 5 of y. That stands as the answer. For number 9, we learned that log base b of a to the p, when you have a power, you can bring the power in front. This is going to be crucial in solving equations in the next section. Bring the power in front. And so log base y of x to the third, 3 here's the power, so that 3 simply goes in front. Log base y of x. Put that in exactly as is written there. All powers come to the front. All powers come to the front. Similarly, here, the exponent is negative 5. This is equal to minus 5, the log of c. All powers come to the front. Now we're going to use them together. And so here is going to get some shorthand together. That again, multiplication turns into addition. Multiplication turns into add. Division, you need a subtraction sign. All powers go to the front. So I'll do this carefully a couple of times and then we'll speed it up. This is equal to, by the first rule, you're multiplying y to the fourth and x. And so we know multiplication means that you're adding. So the log of a multiplication turns into logs of addition, multiple logs of addition. So this is equal to log of y to the fourth plus the log, and this is base b, log base b of x. Right? So because this was multiplication, it turns into addition, and you write logs on each one. And then there's a rule that says something about powers. Here, this y to the fourth has a power. We can bring it in front. So this is equal to 4 log base b of y plus log base b of x. And that stands as the answer. And so we took one log and have expanded it as multiple log expressions. And that's the answer. So, shorthanded notation, to write this quickly, you would just write, it would be 2 logs and a 4 in front because that has a power. So notice the pattern, if possible, as we speed up on these. This is equal to log base 7 of the square root of c, and then there's a log base 7 of 49. You put a log on each one, and now because we're dividing means subtract. Now, the other remark is, mimicking bringing this 4 in front, this square root symbol is kind of weird, but we remember that the square root of a number is just that number raised to the 1/2 power. So really, this is just log base 7 of c to the 1/2, and Lord have mercy, that is a power, and we have to bring it in front. And so using that all powers come to the front, this is equal to 1/2 log base 7 of c minus, and again, this number does not stand alone. Again, the log being the power, when I write log base 7 of 49, I'm asking for the power, the exponent that I would raise 7 to in order to get to 49. I know that 7 to the second power is 49, and therefore log base 7 of 49 is 2. And that is the answer. So we have to be very careful that this doesn't just stand there alone. That can be reduced. More than halfway there in the pages. We're going to bring it all together. Let's see if we can do this. We're going to break this one log into 3 separate logs, utilizing the fact that multiplication turns into addition, division turns into subtraction, and every single power comes out in front. This is equal to, we'll do it the long way first. This is equal to, well, division. We'll do division first. So this is log base b of x to the third y minus log base b of z to the 9th. And then I notice, and again, this subtraction is here because we were dividing. In shorthand notation, all terms in the denominator will have minus signs in front of them. Anything that you're dividing by should have a negative in front. Now, I'm multiplying this x to the third and y, so that, again, this multiplication turns into 2 separate logs of addition. Log base b of x to the third plus log base b of y minus log base b of z to the ninth. And then I notice that some of these terms have powers on them, and then I bring all the powers in front. 3 log base b of x plus this y had no power, so I'm going to leave it alone. But then this has a 9, and then minus 9 log base b of z, and that stands as the answer. And again, look at the pattern. Right? So everything in the numerator has a power, has a plus, and the power comes in front wherever it is. And then everything in the denominator has a minus, and you put the power in front. Similarly here, I'm going to try to do this all in one step. First of all, I'm going to change this square root to a 1/2 power. And then I'm going to give you a second to fill in what you think the answer is following the pattern that we have been using. Let me give you some more space here. This should be equal to 3 logs base d we'll fill it in with a different color. And so here, this 1/2, there should be an x here for log base d of x, and this x had an exponent. All exponents go in front. 1/2 log base d of x. This y to the 8th was in the numerator, so this is log base d of y, and it's a plus because it was multiplying the x to the 1/2. But we also noticed that this y had an 8 on it, and all powers moved to the front. This z is here. It's in the denominator. That means I had a minus, and then there had a power there of 2. That 2 goes there. This stands as the answer. And now I hope that we're seeing the pattern, and we can read it off pretty quickly. Pragmatically, using some of these properties, log base whatever, right? If it doesn't have the base is automatically 10, right? So again, when I write log of x, I mean log base 10 of x. If no base is seen, it's base 10. So again, using the fact that the log base b of a plus log base b of b is equal to the log base b of a times b. Now, before we were expanding logs, now we're going to bring logs back together. Here I'm provided with 2 logs, 1 log here and another log here. And this rule says that I can write them all as 1 log, because if earlier we said that the log of multiplication means the addition of 2 logs, this of course means that the addition of 2 logs turns into the log of multiplication. So this is the log of 100. Again, this is log base 10 of 100. This we should know offhand, because this is nothing but the power that you raise 10 to in order to get 100, and we know that 10 squared is 100. The answer is 2. Here, the natural log of x plus the natural log of 20, again, the addition of 2 logs becomes the single log of the multiplication. So the log of x plus the natural log of x plus the natural log of 20 is simply just the natural log of the product, the natural log of 20. Here, this subtraction means that we're dividing. I can write this as one single log. It's log base 6 of 24 divided by 4. And as you might imagine, that's going to be a nice number, log base 6. 24 divided by 4 is 6. Log base 6 is nothing but the exponent that you need to raise 6 to in order to get 6. That number is 1. 6 to the first is 6. The answer is 6. Putting things together again. So we're going to use a couple rules here. So let's remember log base b of a to the p equals p log base b of a. So I keep saying that you can pull powers in front, but then you can say all powers in front can go back, right? So we're going to reverse the process we had before. I'm going to use that rule first. That this is equal to log of y, and then instead of having the 14 out front, we're going to pull it back. And the reason is because we want to collapse these logs, these two separate logs, into one log. So log of y plus 14 log of z, I can then write, instead of 14 log of z to the 14th, pulling the power back up on the letter. And then now we're experts at this. We know that the addition of two logs means that you are going to multiply. So this is log of y times z to the 14th, and that is the answer we are looking for. We have now transformed two separate logs into one single one. We're going to expound on this pretty quickly. So the shorthanded notation is that you write one log. If it's plus, you multiply the y and the z, and any power you see, you put on the letter that's associated with it. And so hopefully we can see that the answer to this, we'll do it the long way in just a second, but can you guess that this is log base b of what thing? Well, there's an x, and there's an x to the 7th. It's a plus sign, so you're multiplying, and there's a z, and that z in front has a 3. That should be the answer. We'll do it the long way, but as you might imagine, you can start to read these off. This is equal to, well, all powers go back up. So this is log base b of x to the 7th plus log base b of z to the 3rd. And then, as we've been saying the whole time, addition turns into multiplication. And so this follows immediately because this becomes base b of x to the 7, and instead of multiplication with two logs, there's one log, and the multiplication turns into, the addition turns into multiplication. Here's subtraction with the natural log. Again, all powers go in front. Can you see that this would be the natural log of the ratio, because this is subtraction? There's an x to x plus 3, and then that has a power of 6. And then there's an x, and that has a power of 7. And again, this x to the 7th is in the denominator because that's a minus, and that power is 7. Using rules very carefully, this is equal to, using the power rule, bringing the 6 and the 7 up front on powers respectively. You get that. Again, subtraction of two logs turns into one log that features division. We'll put that in. We had mentioned the change of base formula earlier. We said that the log base b of m is equal to log base a of m over log base a of b for any base a that you like. And therefore, it's much nicer to use the log that's in your calculator. And so that means that you would either use the log button, which is automatically base 10, or you would use the natural log of m over the natural log of b. Right? Either one is fine. So in your calculator, this is equal to the natural log of 16 over the natural log of 12. And we'll put that in. There's the ln button there. The natural log of 16. Move this. There's the division sign. The natural log of 12. This is going to be an ugly number. And then now we just need to ask, how many decimal places do we need to round? And it says round to 4 decimal places. That's a lot. And that's annoying. But it's 1.1158. In a similar way, this one is the natural log of 12 or the natural log of 88.5. We'll put that in. assuming that's still four decimal places, it is 0.5543. 0.5543. There. And that might be it. Maybe not. What else do we got here? That is it. Excellent. So next time we're going to use all these rules to solve equations. That's going to be the end of the class, basically. Next week, I would imagine that we start reviewing for the final. I hope it helps. I'll talk to you soon.